In this video, we're going to talk about calorimetry and bomb calorimetry and creating thermochemical equations. So one of the purposes of calorimetry is to define how much heat per unit is necessary for the reaction. All right, so how much heat goes into the system, how much is lost from the system. And we can calculate this value to create a constant that will allow us to estimate energy transfer repeatedly. All right, so the way this works, calorimetry measures the flow of heat, how much heat is gained or lost by the system. And using that same equation that we looked at before, we can then use the heat lost from the system but gained by the calorimeter to determine the Q value for their system. All right, so this relies on a lot of the same things we talked about in the previous video. We're going to look at heat capacity again. We're going to be looking at calculating this Q based on heat capacity and temperature change. All right, and we're going to be using the idea we talked about with thermal energy transfer, that any heat lost by the system is gained by the surroundings, and so they are equal with this little negative sign, all right, indicating lost by one side, gained by the other. Now, calorimeter is a piece of equipment that allows us to have constant pressure and isolate our system from the surroundings. So any heat that we see transferred is not lost to the surroundings. All right, so we're going to focus, instead of on the system, we're going to focus our calculations on the surroundings. And in this case, that is the calorimeter. So our calorimeter, our piece of equipment, is going to represent the surroundings, and we're going to focus on the Q of the surroundings and then apply that to the system. All right. Now, our surroundings we're going to use is found based on the mass, the heat capacity, and the temperature change. So from our equation, mass, heat capacity, temperature change of the solution that we create in the calorimeter. All right. That means the system is defined as the substance we're starting with at the beginning. We are reacting that in the calorimeter, potentially by making a solution. And then that solution becomes the surroundings that we can calculate the Q of. All right. So here's a diagram of a bomb calorimeter. A bomb calorimeter is a type of calorimeter that causes a combustion reaction for the chemical reaction. So down here in this little area, we're going to put our system of choice. So here's whatever substance we're trying to study as our system. We put that in a small dish. We've got ignition wires coming up. There's oxygen in the chamber. And after the ignition wires hit, we're going to see combustion of our sample in the oxygen atmosphere, which, if you remember, your combustion reactions should create our CO2 and our water, sometimes other gases as well. And we're going to see heat transferred from this chamber into the surrounding water. So over here we have water in our bomb calorimeter. We have a stir that spins to try to evenly distribute all the heat in the water. And then a thermometer is used to measure the temperature change. So heat lost by our system into the water or the surroundings or the calorimeter is then reflected as a temperature change, and we can record that and use that value to calculate what Q was, or how much heat was transferred. All right, so here's an example of our combustion reactions. Hopefully you remember this. So we have hydrocarbons, so something containing carbon and hydrogen, or maybe carbon, hydrogen, and oxygen, potentially nitrogen in there as well. In the presence of O2, creates our CO2 and our water. All right. So we define our system as our hydrocarbon and our oxygen. So this is what goes into that little chamber in the calorimeter. That's our system. The water and our products that are created are going to contribute to the surroundings. All right. For a calorimeter, the container or the calorimeter itself also is part of the surroundings. Because it's the isolated system, we can incorporate that into the surroundings as well. All right. Now what that typically means is we're going to have a heat capacity of the calorimeter. Okay, and notice the units here. Kilojoules per degree Celsius. So there's no grams or moles anymore. What they've done is when they have a certain calorimeter, it has a fixed volume, a fixed amount of water goes into the calorimeter, and so we've incorporated that quantity of water into the heat capacity value. Since the water amount is constant each time, we no longer have to use it. So now when we're going to talk about Q of the surroundings, we're just going to look at the 9.63 kilojoules per degree Celsius times the temperature change. All right, we no longer need the M or the amount because it's incorporated in this heat capacity. All right, so let's see what we've got. We put ethanol, 2.84 grams, in excess O2 into our bomb calorimeter. Once ignition started, combustion reaction occurred. The temperature of the calorimeter, which is all that water, rose from 25 to 33.73 degrees Celsius. If here we have our heat capacity of our calorimeter, what is the value of Q? All right, so we're going to use our equation. But this time we don't need M, all right? We don't need M, we've got the rest of it. This allows us to calculate Q of the surroundings. Then negative Q of the surroundings is going to equal the Q of our system. Alright, now it's asking for Q for 1 mole. Okay, so we got to keep that in mind. But let's solve for Q of our surroundings first, because that's what we have information about. The 9.63 times our temperature change. So final minus initial. Alright, and this is going to be a positive value because heat is going into the surroundings. So I get 84.07 kilojoules. Now that means that Q of my system is going to be negative 84.07 kilojoules. Alright, because we have the negative value up here in front of our surroundings to give us system. If heat is lost by the system, we have a negative Q, gained by the surroundings, positive Q. Now it wants to know per mole. The Q we found is actually per, I'll draw the line, 2.84 grams. All right, that's how much we burned. So if we burn 2.84 grams of the ethanol again, we should see the same Q value. If I increase the amount of ethanol, I should see an increased Q value. All right, so the amount matters for the ethanol that we burn. So I'm going to write it like this. We have negative 84.07 kilojoules per 2.84 grams. Now if I want to know how many moles that would be, I'm going to use molar mass. So we calculate the molar mass of ethanol, and I get 46 grams per mole. and our grams will cancel out, and I'll have kilojoules per 1 mole, which is what it's asking me for. So negative 1,361.7 kilojoules per 1 mole. Alright, so that would be the Q value if I combusted 1 mole of ethanol. Even though I didn't combust 1 mole of ethanol in the experimental design, I can still use the calculations to determine how much would be required for 1 mole. Alright, let's try one more example with this. 0.7022 grams of oxalic acid burned in a calorimeter with a heat capacity of 1.238 kilojoules per Kelvin. Temperature increase 1.602 Kelvin. Alright, calculate Q. So again, we're going to start with Q of the surroundings, or the calorimeter. So I have 1.238 kilojoules per Kelvin times my temperature change. Alright, this will give me my kilojoules. So I had 1.983 kilojoules. Alright, so that's the amount of heat that went into the water, into the calorimeter. So that means my system, Q for my system, is going to be the negative of that. Alright, because the system lost heat. And that would really be my Q. So Q for this reaction, bam. Alright. Then it asked me to calculate Q for 1 mole. So this number I got up here is Q based on burning 0.7022 grams of the oxalic acid. So if I burn more, Q changes. So Q is dependent upon how much I burn. The more I burn, the higher Q gets. Alright, so this value of Q is based on a certain grams. Now I can turn that into moles by using molar mass. For oxalic acid, we have 90 grams per mole. Alright, so this gives me negative 254 kilojoules per mole. Okay? Alright, so bomb calorimetry is used to determine heat necessary per gram or per mole that is moved from the system to the surroundings. Alright, so now we need to talk about a few other terms. So we've been talking about heat. In our previous video, we talked about heat and work for our energy change. Now we want to talk about this idea of enthalpy. Enthalpy is a measure of heat change for a system, but it turns out being a more constant value term. Okay, so if we look at our original equation, energy equals Q plus W, it's heat plus work. If we then define work as our negative P times delta V, alright, getting down here, alright, we can see where this equation starts coming from. Alright, so if we isolate Q and say Q is equal to E minus W, so just rearranging what we have, and then I substitute in what W is, minus negative, alright, we're getting very close to what we have written down. So E plus P times delta V, alright, gives us our delta H. Now we're still defining it as Q, but when we have constant pressure, we can apply normal pressures of 1 atmosphere and that being constant, we can apply the ideal gas law. The ideal gas law then allows us to look at enthalpy, which is our delta H, as the Q, or the heat value. Alright, so enthalpy is all of our internal energies for a system plus the work done, pressure of the gas times change in volume of the gas. So we're looking at that rearrangement of the energy equation where energy is heat and work. Now we're defining it in terms of the heat, and we say that the heat of the equation is equal to the energy plus the work that was done. Okay, so we're just rearranged it. But at constant pressure, if pressure is no longer changing, then what we really are saying is that the enthalpy of the reaction is just the Q. Alright? Now we're going to differentiate delta H and Q in just a minute. But what we're doing is using that Q value that we've been able to calculate with our calorimetry, or our thermal energy transfer that we had in previous. We're able to calculate that Q value and use it to find our delta H at a constant pressure. Alright, so a couple of ideas then. We've already talked about heat being transferred out of the system or into the system, and we define that in terms of Q. We're now going to put another term to that, and that is endothermic versus exothermic. Endothermic means that we have a net increase in heat in the system. So heat is going in. So you can imagine this positive Q idea. Exothermic means that heat is leaving the system, going into the surroundings. So this negative Q idea. Alright, and now that we're talking about delta H equaling Q, we can say that endothermic is positive delta H and exothermic is negative delta H. Alright. So when we define a chemical reaction, we can determine whether it is endothermic or exothermic, whether heat is lost from the system or heat is gained in the system. If we have a positive Q, we also have a positive delta H, then we have a net increase in heat for the system. That means heat is coming from the surroundings and going into our system. So our surroundings are going to get colder. We're going to feel colder because they're losing their heat. It's going into the system. Exothermic is the opposite. If we have an exothermic reaction, heat is leaving the system. As it leaves the system, it goes into the surroundings, so our surroundings heat up and increase in temperature. So our negative Q, heat is leaving, gives us a negative delta H, exothermic reaction, and the reaction vessel, the beaker, the test tube is going to feel warmer because the surroundings are going to heat up. Alright, so we have 3 possibilities that could exist. We can have a positive delta H, indicating endothermic reaction, heat going in. We can have a negative delta H, indicating exothermic reaction, heat going out. Or we could end up with a net zero, meaning no heat is lost or gained. Alright. We also can define delta H based on this final minus initial idea that we talked about with energy. And remember, we talked about energy only depends on where we start and where we end. We can calculate a delta E by subtracting final minus initial. Enthalpy is the same idea, our state function. We only need to know the enthalpy of the products and the enthalpy of the reactants to determine our delta H. We can subtract. Now, if you remember, heat was a path function, not a state function. But delta H is going to be a state function. Alright, and we're going to talk about what the difference is. Alright, so when we're deciding whether something is endothermic or exothermic, we need to know what our system is so we can define which way heat is going. So once we define our system, and that can be a chemical reaction, that can be a balloon, that can be a candle, anything we're interested in. Once we define our system, then we can look at which way heat is transferring. So if we think about some common everyday occurrences, like cooking an egg, do I need heat to go into the egg or heat leaving the egg if I want to cook it? And of course, we have to put heat into the egg. All right, if I'm going to cook an egg, I need heat. So I have to put heat in. This is an endothermic process. A candle flame, and any kind of flame or fire, is going to be an exothermic process. We can feel heat coming off of the system. Making ice cubes. So think about what you need to do. If I want to make ice cubes, I have to remove some heat from the system. Right? So if I'm starting with liquid water, I want to freeze it, I have to remove some heat from the system in order for the water to get cold enough to form ice cubes. So this ends up being exothermic. I have to remove the heat. Alright, if I want to melt ice cubes, that requires heat going in, right? If I want something to melt, I have to heat it up. That's endothermic. If I want to make the ice, that's exothermic. Condensation on your car window. So condensation also exothermic, because condensation is taking gaseous water molecules that are in the air, contacting something colder, decreasing the heat that's in those gas molecules till they turn into a liquid. Alright? So turning a gas into a liquid is also exothermic. I have to remove that excess heat. For a chemical reaction, we indicate whether the reaction is endothermic or exothermic in a couple of ways. One way is we can just write the word heat as either a product. Alright, so in this example, it's on the product side. So we would say it's exothermic. It is leaving the system. We write it as a product, leaving. If we put it on the reactant side, then it's considered an endothermic reaction. Heat has to go in order for the reaction to occur at all. So that's one way we can write the reaction, where we have our balanced equation and we just put heat as a reactant or a product to indicate endothermic or exothermic. You would also see it potentially written as the actual number, plus 100 kilojoules of heat. All right, we'll talk about the number in a minute, but that's another way you might see it. The most common way, and what we're going to look at calculating, is by writing out the delta H. So the delta H defines whether the reaction is endothermic or exothermic. So once we have a balanced equation, we might also see a delta H value given after it. This indicates whether it's endothermic or exothermic based on the sign. All right, so this one has a negative sign, so indicating exothermic for this particular reaction. A thermochemical equation, then, is a balanced equation that includes the phases of matter, solid, liquid, or gas, or aqueous, and includes a delta H value for the reaction. All right, notice the units over here. We have joules or kilojoules for our delta H. And it's not per mole, it just says joules or kilojoules. We're going to come back to that in a minute. Alright, so when we talk about the concept of this, let's make sure everyone understands what the thermochemical equation is telling us. For this example, we have 2 moles of H2, 1 mole of O2, forming 2 moles of H2O. And we're listed gases for the H2 and O2, and liquid for the water. We have a delta H value telling us that it is exothermic because of the negative, and kilojoules, so it gives us our quantity. Alright, so this is an exothermic reaction that is going to release 571.7 kilojoules of energy or heat when the reaction as written occurs based on all these coefficients. Alright, so now comes the difference between Q and delta H. Q we've been talking about is an amount of heat. We've been talking about it in terms of joules and kilojoules, and is a quantity. And like we saw before, that quantity can change based on how much starting material I have. If I burn 10 grams, I'm going to get a certain amount of kilojoules. If I burn 20 grams, I'll get more. Alright, so Q can change based on how much you start with. Delta H is really considered more of a constant value, and it is a rate. Alright, so instead of it just being a given amount like Q is, it is a rate. It describes the heat gained or lost per mole from the coefficients, from the balanced equation. So it is saying that if I burn 1 mole, this is the energy that's going to come off. If I burn 2 moles, this is the energy that comes off. Alright, so it's more of a rate as opposed to an amount. So even if I change the amount of my starting material, delta H stays constant. Alright, and so here's a very simplified idea from this. So Q is an amount based on Q is an amount of heat based on the amount of starting material that you have. Okay, and N represents this mole coefficient. Alright, so from that then, delta H could be defined as Q per the mole coefficient. Alright, very much like we were looking at before when we had so many joules per gram that we burned and we turned that into moles. We were calculating a delta H value. Alright, so let's look at an example of this. Sulfur burns an oxygen gas to produce sulfur dioxide. Reaction evolves, which means releases, 9.31 kilojoules of heat per gram of sulfur. Write the thermochemical equation. So at constant pressure then, we have the idea that we can relate the Q to our delta H. And we're given the Q value per gram. Alright, so our Q is 9.31 kilojoules, assuming we burned 1 gram. Now we're trying to get a delta H from this. So we're going to set this up. I'm putting the negative out front because heat is being released. That's what evolved means. Kilojoules per 1 gram of the sulfur. Alright, and then we can turn this to a per mole. Based on the molar mass. Alright. That way our grams are going to cancel out and we'll have per mole. Now the other thing we want to look at is our balanced equation. And we're producing sulfur dioxide. Alright, so we need to balance this. Alright, so we end up with 1 for our coefficient over here. So when we calculate our value then, this is going to be per 1 mole. So this is kilojoules per 1 mole. Alright, so that would be our delta H. So here we have our equation that we wrote. S8 plus 8O2 gives us 8SO2. We have our calculation, the negative, because heat is being released or evolved, 9.31 kilojoules per 1 gram. And then we're multiplying by the molar mass. Alright, our grams are going to cancel out, and that gives us negative 2.39 times 10 to the third kilograms. Alright, so the mole is not written here for the units, it's just going to be the joules or the kilojoules, because we want to be able to apply this delta H to everything in this equation. So even though we use sulfur in order to calculate the Q, we could also find the delta H based on the amount of SO2 that was made, for example. Alright, so this value, this delta H value, not only says that we have 2.39 times 10 to the third kilojoules released per 1 mole of S8, but it's also per 8 moles of O2 and per 8 moles of SO2. So we don't put the mole on there because we want to be able to apply it to anything in the equation. Okay, we leave the negative because that indicates exothermic heat is leaving the system. Putting that all together then, we have our balanced equation, we have the phases for each of our substances, we have the delta H value that we calculated. So this delta H value can now be used to calculate how much energy or heat is coming off the system for any amount of sulfur that we start with or O2 that we start with. Alright, let's try another one. We have nitromethane, burns an oxygen gas to give us CO2, H2O, and N2. We have 20.03 kilojoules of heat coming off of the reaction if we start with 1.724 grams of our nitromethane. We want to write our equation, we want to calculate delta H. Alright, so let's start with the equation. We have CH3NO2 burning in the presence of O2 to give us CO2 and water and N2. Alright, so we want to balance our equation. However you want to balance it is up to you. There are, of course, a couple different tricks you can do with combustion reactions especially, but you need to be able to balance the equation. So I'm just going to put in the coefficients because we're not going to focus on balancing right now. But definitely if you struggle with that, you need to go back and review it. Alright, so there's our balanced equation. Now we want to calculate delta H. So here is our Q value. I'm going to put a negative out front because it's released. So negative 20.03 kilojoules released per the 1.724 grams. Alright, so this tells us the Q value coming off based on our starting material. We want a per mole value, so we're going to use the molar mass of our nitromethane to convert our grams into moles. Alright, so this is molar mass. Our grams are going to cancel out. The last part is going to be about the balanced equation, about this coefficient, because this tells us the kilojoules per 1 mole now. But based on our balanced equation, we didn't burn 1 mole, we burned 4 moles. Alright, so I'm going to multiply by 4. So this gives me negative 2,835 kilojoules. And this is our delta H value. Alright, so I used nitromethane information because that's what I was given, but I can now apply this delta H to anything in the equation. Alright, so that's the value of finding delta H. It's now not just about the nitromethane, it's about anything in that equation. Alright, let's look at using the delta H value too. Delta H value is a rate. It's also a conversion factor. Okay, delta H is a conversion factor between our energy or heat and moles. Alright, so in this example we have hydrogen peroxide decomposing and we have a delta H value. How much heat will be released? So I'm looking for Q. If 1 gram of hydrogen peroxide decomposes. Alright, so I'm going to start with my 1 gram. I need to relate that to my delta H, so I have to do that through moles. So the first thing we want to do is turn my hydrogen peroxide into moles. So dividing by the molar mass. Alright, once we do that, now we have moles of H2O2. We're trying to get heat, but now I can use my conversion factor. Negative 190 kilojoules per 2 moles of H2O2. This is like using your mole-to-mole relationships with a balanced equation. That delta H value is just part of that. Alright, this will then allow me to calculate kilojoules because my moles cancel, my grams cancel, and I have negative 2.79 kilojoules. So 2.79 kilojoules of heat is being released from that 1 gram. Alright, so we can use delta H as a conversion factor. Let's try another one. So we have our thermochemical equation, we have delta H. If we know we need 74 kilojoules of heat to heat up our cup of tea, how much methane should we burn to get this? Alright, so this time we know the Q, and we're looking for the amount. So we're going to start with 74 kilojoules. We're going to use our conversion factor to turn kilojoules into moles. So I'm going to put the kilojoules on the bottom so it will cancel out. I want to relate that to the methane, which has a coefficient of 1 in our balanced equation. So I have negative 890 kilojoules per 1 mole of methane. And then since I'm looking for mass, the last thing I want to do, multiply by the molar mass. Alright, I'm going to put a negative in front of the 74 because that is heat that is released from the system. And then the negatives will cancel out because of course mass is positive, 1.33 grams. Alright, so we can calculate heat that is changed. We can calculate Q from delta H. We can calculate mass or amount that we would have to burn or react in order to get a certain quantity or a certain amount of heat. Alright, last one, we're going to circle it back around to what we initially started talking about with this one. We have 5 grams of butane. It's burned in oxygen, 247 kilojoules of heat are released. What is delta H? So this is Q. Alright, the 247 kilojoules is Q, and it is based on the 5 grams. So released means negative 247 kilojoules per 5 grams of the butane. I need a value in terms of moles for delta H. So I'm going to convert using the molar mass, 58 grams per 1 mole. Now the last thing I need to know is the coefficient of butane. So this is where we have to look at our equation. We're burning this in the presence of O2, so this is our combustion reaction. Again, we need to balance it. Alright, so however you want to balance, again, that's up to you. We're not going to focus on that with this video, but you need to know how to balance. Alright, once we have it balanced, we have a coefficient of 2 in front of the butane, so I need to multiply by 2 to get my delta H value. Alright, so negative 247 divided by 5 times the 58 grams per mole times 2 gives me negative 5,730.4 kilojoules. And this would be my delta H value. And of course it is exothermic, like every other combustion reaction. Okay? So these just take some practice. The more you do, the more it becomes sort of second nature and you get much quicker at it.